This is the last video on section 4.2, and in this video I'll be talking about concavity and the second derivative. So one of the things we already talked about is that the first derivative tells us about whether our original function is increasing or decreasing. Our function f is increasing if and only if f prime is positive, and the function f is decreasing when the f prime is negative. We can apply this principle to the function f prime itself. So when f is increasing, f prime is positive. So we can apply that to f prime so that we say when f prime is increasing, f prime prime, in other words f double prime, is positive. It's the same principle just applied to the function f prime. Similarly, we have when f of x is decreasing, f prime of x is negative. So when f prime of x is decreasing, f prime prime, f double prime of x is negative. Again, the same principle just applied to the function f prime. So what I want to do is talk about what does this mean? What does it mean to say that f prime is increasing or that f prime is decreasing? What does that look like on a function? So here's a function where f prime is increasing. Let's think about why that is. So over here on my function, I've got a big negative slope. So that tangent line is pretty steep and it's got a negative slope. But as I move to the right, that tangent line is leveling out, which means the slope is still negative, but it's moving up towards 0. At this point, we have a critical point, so we have a slope of 0. And then once I'm past that point, my slope is gradually increasing. So what I get is this sort of U shape when my derivative is increasing. And we say that this function is concave up. So concave up is just what it looks like when a function has an increasing derivative. So this graph here is a graph of f. So when f prime is increasing, as we're seeing here, what we're saying is that f is concave up. Now it can only look like one side of this. It could just look like that, or it could just look like that, or it could look like the combined U shape. But that's the idea. When f prime is decreasing, same basic idea. Here I'm starting with a big positive slope, and then as I move to the right, my tangent line is leveling out, my slope is decreasing, my slope is 0, now my slope is going into the negatives, now it's going deeper into the negatives, so my slope is decreasing. Again, the function we're looking at here is f, so when this happens, when f prime is decreasing, we say that f is concave down. So that's just visually what's happening when our function has a decreasing derivative. And again, it could only just look like one side of that. It also could look like just that side, or it could look like the combined upside down U shape. So putting this together, we have really what the second derivative tells us. So when the second derivative is positive or negative, that tells us whether our original function is concave up or concave down. So this is the sort of full picture of what the derivatives tell us. F prime tells us about whether our function is increasing or decreasing. F double prime tells us about whether our function is concave up or concave down. So to just do an example, here we have a function and we're looking for the intervals on which this function is concave up or concave down. So we're looking for the intervals on which f double prime is positive or negative. So this is going to be really similar to what we did before when we were looking for intervals when f prime was positive or negative. In other words, when we were looking for intervals where our function f was increasing or decreasing. We're going to find the places where our second derivative is 0, and then in between those places, we're going to test and see whether f double prime is positive or negative. So our first step here is going to be to find the points where f double prime of x is equal to 0. Or, and again, this doesn't come up too often, but or where f double prime of x is undefined. We're not going to have to worry about that for this function because it's a polynomial, but every once in a while that might come up. So if we're going to need to look at f double prime, the first thing we need to do is figure out f prime. So we take the derivative of negative x to the fourth, that's going to be negative 4x cubed. The derivative of negative 2x cubed is negative 6x squared, and the derivative of plus 12x squared is plus 24x. And now we're going to take another derivative, right? We need to find f double prime, so that's going to give us negative 12x squared minus 12x plus 24. As I said, that's a polynomial, so it's never undefined, so what we're looking for is trying to figure out where does that equal 0. So I'm going to factor out a negative 12. That's going to give me negative 12 times x squared plus x minus 2. And then I can factor x squared plus x minus 2. That's going to be x plus 2 times x minus 1. And so that's going to give me two solutions, x equals negative 2 and x equals positive 1. Now for step 2, we're going to draw a number line. Just like we've done for the first derivative, we're going to draw a number line here. On my number line, I'm going to put my two values that I found, -2 and 1. And then in between those values, I'm going to pick a number less than -2, I'm going to pick a number between -2 and 1, and I'm going to pick a number bigger than 1. And what am I going to do with those numbers? I'm going to plug them into f double prime. Because remember, my goal here is to figure out whether f double prime is positive or negative. I know that f double prime is 0 at these 2 points, so what I now need to know is what's happening in between those points. So let's pick a number less than -2. How about -3? So f double prime of -3, that's going to be -12 times -3 squared minus 12 times -3 plus 24. And again, I'm going to put all that in my calculator, and that's going to work out to be -48. Continuing, now I need to pick a number in between -2 and 1. How about 0? F prime of 0, again, I'm using my calculator here, that works out to be 24. And then let's pick a number bigger than 1. How about 2? And again, I plug in 2, and I get -48. So less than -2, my second derivative was negative. In between -2 and 1, my second derivative was positive. Greater than 1, my second derivative was negative. So my conclusion, right, so we do all this work, we don't want to end the problem without actually figuring out what we learned. My conclusion is that my function f is concave down. So concave down is going to be where f double prime was negative. So that's going to be on the interval from -infinity to -2 and from 1 to infinity. And then f is concave up. That's going to be where we found the plus signs. That's going to be on the interval from -2 to 1. So that's how we do a problem like this. We're looking for the intervals on which our function is concave up or concave down. First, we're going to find the points where the second derivative is 0 or undefined. Then, much like we did before, we're going to draw a number line, picking numbers in between to figure out if the second derivative is positive or negative, and then we draw our conclusions. So now, those points that are in between, those points at which my second derivative is changing sign, we know that for the first derivative, if the first derivative changes sign at a critical point, we have a local maximum or a local minimum. When we have the second derivative changing sign at a place where the second derivative is 0 or undefined, we call that an inflection point. This is sort of relevant to thinking about, when we're talking about the coronavirus right now. So if we've got our graph of time and infections, the graph currently is spiking up, and what we're looking to try to do is to let the graph level out. And so this point right here, that is actually an inflection point. So that's what people who are studying this are looking for. We're hoping that sooner rather than later we get to this inflection point, because over here my graph is concave up. The rate at which my number of infections is increasing, right? My slope is increasing. And so what we're looking for is to hopefully get to the point where the graph is going to be concave down, where, yeah, the number of infections is still going up, that's bad, but the rate at which they're going up is slowing down. And so the concavity changing at this point has this real world sense of what that actually means. So this also leads us to something called the second derivative test. This gives us a different way of testing a critical point to see if we have a local maximum or a local minimum. So what this says is that if we have a continuous function with a critical point, if the second derivative is positive at that point, right? So we're not plugging in something above and something below, we're actually plugging in that exact number. And if we get a positive result, then that gives us a local minimum. If we plug in that number and we get a negative result, that gives us a local maximum. And if we get 0, then unfortunately this test turns out to be inconclusive in that case. It doesn't tell us what's going on. So let's break down each of these 3 cases to understand why this second derivative test is saying what it's saying. So the first thing says that we've got a critical point, right? So we've got a point where we have a horizontal tangent line, that's happening here. And our second derivative is positive because our function is clearly concave up. It's got that U shape. So our function's concave up, we've got a flat tangent line, and we can see here that our function has a local minimum. If instead we had a critical point, again, we've got a 0 slope here. If again we had a critical point and our function was concave down, which it clearly is here, concave down looks like that upside down U shape. So if our function's concave down, then we have a local maximum. And if the second derivative is 0, then really anything could happen. So here are 3 examples of functions where we have a critical point. All of these have critical point at 0, 0. And all of them have a second derivative that equals 0 at that point. And feel free to try that yourself. If you want to take the second derivative and plug in 0, you're going to get 0 for each one of these functions. But the problem is, here we have neither a max nor a min. In this middle picture, we've got a local minimum. In the third picture, we've got a local maximum. So really anything can happen. So unfortunately, if you get to that point where you're trying to use the second derivative test and you end up getting a second derivative that equals 0, you're going to have to go back and then use the first derivative test to test that critical point to see if it's actually a max or a min. Okay, so let's try one more example. We're going to use the second derivative test to find the local extrema for this function. So remember that the local extrema are going to happen at critical points. So in order for us to find these local extrema, first we need to find the potential maxes and mins. In other words, we need to find the critical points. So find the critical points. And remember, those are going to be where my first derivative is equal to 0. So f prime of x, that's going to be 15x squared minus 60x. Derivative of 10 is 0. This is never undefined, so we'll set it equal to 0 and solve. I can factor out a 15x. That's going to be 15x times x minus 4. And that's going to give me 2 solutions, x equals 0, x equals 4. Now, this time, when I'm going to test the critical points, before what we were doing is we were drawing a number line. And we were plugging in something above and something below and figuring out whether it changed from positive to negative. Here, we're not going to do any of that. Now what we're going to do is we're going to use the second derivative test, which means we need to find a formula for that second derivative. In this case, the formula for the second derivative is 30x minus 60. And again, rather than plugging in something above or something below, we're going to actually plug in these values that we found directly into the second derivative. So I'm just going to compute f double prime of 0, and I'm just going to compute f double prime of 4. So f double prime of 0, that's 30 times 0 minus 60, that's negative 60. And that's negative. So if I look back at the different bullet points in that second derivative test, feel free to rewind the video to take a look at that. So that's negative, and that means that I have a local maximum at this point. And then f double prime of 4, that's going to be 30 times 4 minus 60. That works out to be positive 60. That's positive. And so again, by the second derivative test, we've got a local min. So in this case, the second derivative test was a lot easier. And in general, if all we're interested in doing is finding whether or not we have a max or a min, it's up to us to choose which test we want to use. We can choose to use the first derivative test. We can choose to use the second derivative test. Generally, and in this case, the second derivative test was pretty easy. It wasn't hard to compute that second derivative, and it wasn't hard to just plug in that single number and see if we got a positive or a negative result. So very often the second derivative test is easier to use, but there are some situations when it's not the right choice. One situation would be if it would be nasty to take your second derivative. So let's say the first derivative involved the quotient rule and chain rule and all sorts of rules, and you got a really nasty looking first derivative, and you don't really want to take a second derivative of that, then that's probably a time that you wouldn't want to use the second derivative test. Another possibility is that you may try to use the second derivative test, but when you plug in, you get 0. And so in that situation, you'll have to go back and use the first derivative test. So it's really up to you to decide which test you want to use. And in the next section, we're going to be talking more about applications of finding maximums and minimums. And we're just going to sort of pick and choose which test we want to use depending on the situation.